So you are my heroes. Still listening to test. Good, good. So today what we're trying to do is understand how we should approach testing the C++ layer of an app. The complexity of the app depends on your project, but we'll face simple scenarios and complex scenarios. Very quickly, I am an SDM in Amazon, so on paper I don't code. Actually I code, and that's good. I work in a Kindle team, so my day-by-day job is moving between iOS, Android, e-reader, desktop, and managing a team that deal with the C++ layer that render the page that you see on the screen. So every time that you open a page and you see something bad, you can blame me. That's a good thing to bring out from this conference. I'm also the organizer of DroidCon Boston and of SwiftFest Boston. So like it or not, I deal with both platforms. I have a preference for Android, of course, but you know. So today we're taking a look to native code in Android, the JNI wrapper. We'll understand how to test across architectural boundaries, because that's the problem that we're trying to solve. And how we can approach the test of native layers. There are several things that we can do. Disclaimer, my opinion are my own. I'm not representing Amazon here, so I can say whatever. And I use a lot of animated GIF, so be advised. Cool, warm up. So the first debate should be, the question should be what we're going to use, Java or Kotlin? Well, I would say Kotlin, but I leave it to you if you want to go with Java. Kotlin, it's null safe, it's very concise and elegant, it's shipped with a standard library that is super powerful, and work with both object-oriented programming or functional approach. You can mix both of them, you can take advantage of both of them, support lambdas, delegation is supported out of the box, and asynchronous programming as well. If you want to stay with Java, good luck. It's interoperable, so again, please use Java as much as you want, but don't be scared about C++. C++ looks scary. There are C++ developers in the room? OK, it's scary, come on, right? It's not the most, the syntax is nice. It's also very semantic. Come on, the H files are OK. They describe exactly, if you use them properly, you can have a clear description of what your class is going to do. Pointers are not so friendly, but when you compile, that's the problem of C++. It's painful. There is no way to say it differently, because it's complex. The compilation varies for every CPU, and you really start to go deeper. And when you see people that complain about Android Studio not compiling, you say, come on, that's a dream. Come in my world. But why it's complicated in Android? Because it's an additional layer. So whatever you do, whatever app you do, every time that you get out of the Android code, you are interacting with a native layer. And to speak with this native layer from the virtual machine in which your app is running, you're using another layer. This layer is known as JNI, Java Native Interface. So that's true in both scenarios. This is a simple app. And this is when you test. When you test, you have this JNI that is in the middle. So create problems, because it's an additional layer. So for the C++ developer, this will be an easy set of slides. But why we want to use C++ in Android? Because C++ is fast. It's extremely fast. And to do anything that is rendering, to do anything that is sound, to do anything that is video, that's the key. You want to be fast. There is a lot of multimedia libraries that are written in C++. Why we should reinvent the wheel are over there. They're a little bit old sometimes, but they work. I usually hate my project managers when they say, but it works. That's the case that I say, well, it works and it's OK, because I don't want to go too much deep into this multimedia, drivers, whatever. And when I see my developers, I have a team of fantastic engineers. Sometimes we got some exceptions, also in the test report. And you look at that exception, and you say, OK, what the fuck you're trying to tell me? Sorry, but I'm confused. What are all these numbers? And that are memory address. I don't want to get too much deeper. So Then you do this because you want to write cross-platform features. How many of you have had the challenge of writing a cross-platform app? Everybody, right? It's the dream of everybody. Java, write once, run everywhere, then run in Android and on the server. OK, that's almost everywhere. But with C++, you can really write a lot of code that is platform independent. It's at compilation times that things change. Then you can have peculiar bugs that vary platform by platform. But you can make it. You can use the Android NDK, and you can use the Java native interface. What is the Android NDK? The Android NDK is, when you download it, it's a big, massive zip file. But it's a rich tool. It's a folder that is rich of tools that work with C and C++. You have, through the Android NDK, you can have physical access to some of the Android components. You can debug. You can run your test. While the JNI, it's simply the interface that is in between, the layer, the man in the middle. The guy that gets a message from Java and say, hey, you have to call this native function and then execute the function. And vice versa. When you want from C++ to call Java, you still use the JNI. So it's a bidirectional facade. In Android Studio, if you want to add support for C++ to your project, it's enough to pick include C++ support and go ahead. Easy, right? Oops. It's so easy that sometimes you forgot about a couple of exceptions. There is the runtime type information support and the exception support. It's usually good things to add. Otherwise, you will never understand deeply what is going on. If there is an exception, you have much more granular information. It's much more simpler today using C++ inside Android. For instance, in this scenario, there are a lot of dynamic libraries, shared libraries that are coupled together with the app into the JNI libs folder and are divided by architecture. This was the configuration that was up to Android Studio 3.0. Now everything is in the C++ folder, so can vary, but it's much easier. Because you can use Gradle, for instance, and you can configure Gradle in such a way that you can use all the C++ flags that you want, and you can specify what you want to compile. The CMake list, it's exactly the definition of what you want to compile, where are the files, how to link them together, and so on. CMake it's a tool that you use to compile your code. It's platform independent, but let's keep it simple, right? KISS, keep it simple, stupid. So what you need to know to start, it's you add the library, you specify the name of the library, you say that it's a shared one, and you can specify the files. For instance, native lib is the default one of Android Studio, and Lomario is a file that I created. Of course, I'm Italian. I don't want to disappoint you, so I have to use an Italian name in my slides. And you can say to CMake that you want to search for some libraries. In this case, for instance, we are searching for the loglib library. And CMake will find for you automatically the libraries that are embedded into your Android NDK folder. You can compile your code from Android Studio. You already know how to do it. You can use CMake, or you can use NDK build. In the case you use NDK build, you usually have an application MK file and an Android MK file. Both of these files are make files that explain and describe how you want to compile this C++ layer into your APK. Good. JNI wrapper. That's the other component that you need to know. General tips. Don't do too much marshalling between one layer and the other. You can do it. There is nobody that is preventing you, no warning, nothing, but it's slow. And when you use C++ in Android, most of the time it's because you want performances. So be advised, passing data structures around, it's not so efficient. And avoid direct asynchronous communication. You can use multiple threads on the JVM, and you can make it happen anyway. And try to keep the JNI interface small and modular. I saw JNI interfaces of more than 900 lines of code. That's not maintainable, because the next time that you need to add a feature, you will not read it in 100 lines. You will add simply another function. And the reason why it's the naming convention. We'll go to it. So every time you call a native function from Java, or let's say from Android, or from C++ into the Java virtual machine, you pass around a JNI env. It's a pointer to the JNI functions. And these are a lot of functions that you use to convert a data structure, to manipulate string, whatever. And let's take a look to some code. So here we are loading the library. Be advised, if you use load library, it's a relative path. Android Studio will search automatically into your C++ layer, will search for the library that CMake is compiling. If you use load, you need to pass an absolute path. You create these, yes, you load the library is now available, and then you usually create a wrapper. The wrapper exposes some functions. In Java, it's native. In Kotlin, it's external. So be advised, if you see native or external, that's the difference. Say hello to a JNI, it's the default method that is created with Android Studio. Say hello from Mario, it's the variation. The method has this wonderful naming convention. I hope one day to meet the guy that decided that this was a good idea, because for me it's very unreadable. This is Java, then this is my package, then the class, and then the name. And just in case you want to make things complicated, if you are overriding a method, you will have 2 underscores. You get the JNI environment, and simply converting a string into a set of characters, and I'm returning what this C++ function is doing into my Java layer. Naming convention, prefix Java, fully qualified class name, underscore, mangled method name, and then just in case you want to complicate your life, 2 underscores. So keep it simple. Keep this file simple, otherwise you will go absolutely crazy. To use the method, it's simple enough. That's plain Kotlin, nothing special, and that's straightforward, right? Let's try to add a test. But before adding a test, a couple of consideration about TDD. All of us know the TDD cycles, right? So you should follow them. No code without a failing test. Write just enough code to make the test pass. Refactor the code and implement the business logic. About this point, once I was very extreme, I got a method, there was a JavaScript web app. There was a method that was supposed to return a Boolean. I simply write the code, return true to make it pass, and then move to the next method, and the coworker say, hey, what are you doing? It's green, I can move next. No, you should stay in that method. So be advised, stay in the method, implement it, fix it. Then you will have all the time to clean up the code. Try to be very specific with your test. Don't write a generic test, like it should return a Boolean. Yes, in which case, and which Boolean, true or false, should return true if the user is not logged in. Fantastic, write a long method like this, be specific. And decouple the code to support the specificity of each test. This means that you will write more tests. And do this until you don't get blocked. So when you cannot split anymore your code in smaller units, stop. You are almost there. Why you should do this? Because you are validating your architecture. You have to pause and consider if all these functions, all these methods they still have to be together, can be split, move it around. And you have to try to use tests to improve your architecture, because you have some boundaries in a scenario like the one that we are talking about. We have Android, we have JNI, and we have native code. The more you mix these three layers, the more problems you have. The scenarios that you can find usually are a JNI wrapper that uses some native code, very simple, a JNI wrapper that uses multiple libs, complex Android and C++ integration. Let's do this. So the JNive wrapper, when it's a single wrapper, usually you're limited in scope. It's pretty simple. Maybe you need some additional information, or you have a fantastic algorithm that you find on some paper that do the math that your app really need, and it's super fast. That's pretty convenient. It's not very complex. You can have some code into it, and you can write a simple test. The test, say, use the C look. So we have the wrapper. It's still the same wrapper of before, and we're simply asserting that two strings are not equal. Doesn't work. A simple test like this doesn't work. Why? Because the library that you're referring to, it's a shared library, and it's not loaded in the test. So there are alternatives. You can have a conditional execution of the code, or you can mock the native interface. Using an interface, you basically use the interface to describe the methods that your wrapper is going to expose, and then you mock the interface. Fantastic. You can do it. Until it's simple, it can probably work. You move the loading in the wrapper, and that's it. You can add a runtime conditional. That's an interesting approach that can have a very complicated side effect. So we're moving the load is now in a companion object that is the equivalent of a static method in Java, and we're using a try-catch. So we are trying to instantiate the native wrapper, and this native wrapper, when it throws an exception, is returning the native wrapper mock. Okay? Tests are green. If you do this, test works. But that's wrong. We're not testing our code. We're testing a mock. We're testing a mock that if there is a runtime exception, is returning us another object that is not really the object that we're interested to test. So let's try another path. Let's go with the instruments test. Instruments test, you simply write the test. We are asserting true that the string returned from this hello from Mario contains the name that we're passing, and the test works. We're quite there. What's the problem? It's slow. It's terribly slow. When you use the instrument test, you are really committing to have a long execution time for your test. Running a unit test, it's in memory. Running tests with Roboelectric, it's slower, but it's still in memory. If you want to use instrument test, it's fine, but that should be the continuous integration environment. And if the tests are not executed on your local machine, then you're not doing any more TDD. You are simply pushing code on a pipeline, on whatever, and you are waiting for your CI to tell you, hey, there is a problem. And you are a C++ developer. Can you tell me the average time of compilation that one of your projects have in continuous integration? It's minutes or hours? Eight hours. I can tell you the same. I can tell you the same. There is an app that I'm working on that takes also 8 or 9 hours. It depends. So if you delegate the execution of the test to this layer, you will write your code, you go home, and in the morning you see the results. That's terrible. That's why then developers start to smoke cigarettes again. They have to wait big waiting times. That's why also are called smoke test, just for your information. So we have two alternatives. We can mock the JNI layer and run a unit test, and don't write unit test. So no, I haven't said that. Come on, we cannot live without writing our test. Roboelectric. Roboelectric is a potential solution to part of our problems. Why? Because in a nutshell, it's a desktop version of the JVM that Android use to run your code, to execute your code. It's faster, for sure, and can be also integrated using in your continuous integration environment. So it means that you can use kind of the same platform, test platform, in your desktop and in your continuous integration environment. And actually, every platform can be used in both, but Roboelectric, it's kind of fast, and you can have a better experience. The advantage, it's fast. It's an abstraction layer of the Android API. It's very useful because it runs in memory, doesn't open in simulator and anything else, but there are gotchas. It's executed on your local machine, so any test that implies the interaction with the device should be mocked, faked, whatever, but it's not real test. Second, you are mocking some code that are not owned by the app or by yourself. You are mocking the Android platform. And if you remember a book, Growing Object-Oriented System, it's from Addison Wesley. Maybe it's 25 years old or something like that, or 20 years old. There is a recommendation that says you shouldn't mock the code that you don't own. Because given that you don't own it, how you can mock it? You probably don't have the full understanding of the behavior. By the way, Roboelectric is doing a great job. I'm not advocating to don't use Roboelectric. I'm simply pointing out which are the problem. And the test environment could be error-prone. Of course, Roboelectric is a software, right? If there is a bug in Roboelectric and you're pulling your dependencies as a good developer here and there, you can have fake tests that are start to fail. And maybe something changed in the Roboelectric API. And then you go into the update paralysis that is typical of the C++ environment, where you look at people that is still working with Xcode 8, and you say, why? Well, I'm scared. About what? Everything could break, and then I need 2 days to set up again my environment. Anyway, also here, native libraries will not work out of the box. You have to do something. Yes, the situation is not the best, and neither the easiest one. OK, let's take advantage. Whoa, my slides. OK, yes, let's take advantage of the Android NDK. Why? So the problem that we have and that we need to solve is that at runtime, during the test, our shared library is not loaded because it's not in our system. When Android Studio compile also in the simulator the app, it's in the simulator. So when you run the tests that are in your machine, this library is not there. So what you do usually? You usually start to grab some libraries. So if you remember, we said that we have a lib native lib in one of the CMake file that we saw. We usually copy this into the test folder, and we try to load it. As soon as you start to load it, you will see that there are dependencies that are not found anymore because CMake is not compiling anything here. We can also work on a CMake configuration and having CMake compiling here, but it's a little bit more complicated. And then you start to have more than an application class. So you have your app. So instead of starting with an activity in your app, you create an application class. Why? Because in the application class, you create a method that is open. It means that can be overridden in in another class that instantiate the libs manager. That is the famous file that we saw at the beginning that loaded the libraries. Then you create a Roboelectric application. And the Roboelectric application, it's extending this simple JNI test application. And we are overriding the initialized native wrappers. Instead of loading the wrapper or instantiating the wrapper, we go manually and we load our libraries. So we simply get the libs that are in our dependencies. We got the absolute path. We move all these path into a list, and then we load them in a for loop. Now, when you want to test the code, nothing will fail. OK? So There is some manual work, but you can make it. It's way, way, way better. But there is more. There are still problems. So also this one, it's a case where we have a C++ layer that is simple enough. There are more complex scenarios where we should start to think how we really want to keep separated the boundaries of our applications. In fact, we said at the beginning, we have Android, we have JNI, and we have the C++ layer, the native layer. So if we go back in the TDD cycle and we start to create small methods, small functions, we start to decouple and reorganize our code, we should reach a point where we have the C++ layer that can be tested by itself, the Android layer that can be tested by itself, and the JNI layer that really need minimal test, like, for instance, preventing that the crazy naming convention gets screwed up and you get a runtime exception when you're running your integration test in your CI environment. So if you reach this pretty ideal scenario, you can start to introduce Google Test. Google Test, it's a testing library. It's built for C++. It can be used for several layers, because it can be used for unit, for integration, and for acceptance test. It's very nice that you can also specify how big is your test. There are annotations like small, medium, large that you can use in front of each of your tests to simply say if the test takes seconds, minutes, or hours to be executed. And that was nice because in the documentation they really mention hours. So when I read it a while ago, I was pretty impressed. It's used by several projects that have kind of a lot of users, like Chromium or like OpenCV, LLVM, and so on. If you want to write a simple test in using Google Test, you can use this naming convention. Test, it's a macro, actually, and then expect echo, it's another macro in C++, that it's verifying that the string hello world is exactly what gets returned by this method. You have more dependencies. There is an efficient way to mock dependencies in Google Test that is Fake-It. You know Fake-It as a project? OK. I found it very brilliant. Why? Because every time that you have whatever virtual method in any of your C++ classes, you simply create a mock using this word. You do mock, data type, mock. That's it. You have, in a single line of code, a full mock of your class. It means that you don't have to manually mock any of the methods. On top of that, Fake-It exposes several keywords like return that is saying when you are calling whatever method, actually whatever method, the method foo on mock, and it's a method, then please return 1. So you can be very expressive, and that's unusual for C++. At least I find it very expressive. And you can fake and mock whatever you need. Then you can load the test. And that's part of the Android NDK project. You can use the NDK build that is a very efficient way to build code, and then you can use ADB to push the code into your own device or onto your own emulator. And you can execute this test with a single line of code. So what is interesting here is that also if it's complicated, you can, for sure, have your C++ layer being live in Android Studio. If you are an Android developer, I don't see any good reason why you should open Android Visual Studio or another tool to write C++. You are in a single environment. You can add these script to be executed from Gradle as bash files or whatever you want to be. If you want to use that ZSH at the end, a bash file works anyway. And you can have a very clear feedback. If one of these tests, by any chance, depend on any hardware of your device, you should ask yourself the question, is the right test? Is the right dependency? And if it really is, well, you can run the test on whatever emulated environment. The reports. These tests are fantastic, right? But how you can get an output? There is an open source project, Android GTest driver, that basically grep from using ADP all the log of Google test and return you in your shell a fantastic report. You can also use a GTest driver to to save the output in a file. Basically, the architecture, we're not going into the details, don't be worried, but it communicates with the ADB with the device, grab the log, and store all the logs for you whenever you want. It's a Python script, can be executed and used on Windows, Linux, and Mac. I made a pause. Well, done. So we know how to run the test now. We are ready. We have the C++ layer that is fully covered. If we have a dependency, we go on the device. And we can go on the device with our command line. We are using cross-platform tools so far because we are using CMake, can run on every platform. We are using Android Studio, it can run on every platform. We are using Python because a lot of the utilities that you find in the NDK are in Python. And I think that we are in a decent scenario. So, wrap up. It's not an easy process. Testing your native layer is not an easy process. So don't think that if whatever you want to do in 1 hour is done. It takes some time. Also because the compilation time, the configuration varies between each system. And how many of you use Linux at work? OK. That's good for C++, for instance. And it's also good for Android. If you use Mac, you will have a lot of surprises. If you use Windows, who uses Windows? Come on, so really? You use Windows? OK, if you use Windows, you will have even more surprise. So it's not an easy process, but it's reusable. Once you make it work, you can move it around platforms. Because the NDK, for instance, it's including for you a lot of libraries already compiled for every architecture. So whatever library is missing and you need to include in your project, you have it for Windows, for Mac, for Linux, for 32-bit, 64-bit. So that's safer. CMake, by default, work on all the platforms. And whatever you do, whatever you make it happen on your laptop, can work almost the same on a CI environment. It's powerful. Your tests are really covered. Your app is really covered. You can have instrument tests to test the UI, fantastic. But let's talk about under the hood. You can have unit tests to cover the business logic of your Android app. You can have eventually a kind of integration test where you are testing that the facade that your JNI layer describes is consistent with the C++ layer. And you can have the C++ layer running autonomously as a test. And optionally, this test can be run, again, in your local machine, on an emulator, or on a connected device. Questions? Sure.
I got 2 questions. So, this might be outside the scope of it, but I hear that also Rust can also be supported for the NDK. Do you know anything about that?
No.
Okay. Second question is there like good documentation of both?
Oh, yes. There is an interesting book that is Mastering JNI, Mastering Android NDK. It's from Pact. Usually Pact doesn't do great books, but this one is good because explore the problem of going in very deep on Mac, Windows, and Linux. and expose a lot of techniques and gotchas that you can find. There is also another book that is pretty old. You cannot find it, for instance, in digital. You can find it only printed. That is Mastering the JNI. It's blue cover. I have it saved somewhere. I can give it to you, the link, after the talk. Other questions? Sure.
Would you recommend any mechanism for just testing like the JNI legs? Because C is saying you could drive the tests from the Java side through JNI and force it to load the libraries, right?
Yes.
I think some people might say, like, how do you just test that layer and rely on Vue tests to do all the insights here and Android testing to the top?
Yeah. So the question, if I understood correctly, is how to handle the case in which where I showed that you can load the library in Roboelectric, and I don't want to load the libraries because I don't think that it's 100% accurate, correct?
Or you want to load the libraries for, like, not do the full logic of what they do, but just test the layer itself.
Well, if you load the library, it's not because you want to test the entire logic of the library. It's because you want your app to don't throw an exception when it's executed in Roboelectric. So this technique of loading the libraries prevent the app from failing in Roboelectric. And if you want to skip any test of the JNI layer, in any case, if you don't want to modify your code, you have to do it. The native wrapper example that we saw, if you remove the native wrapper from the picture, you are not getting anymore the exception. But if you remove the native wrapper from the picture, you are not testing anymore your code. You are testing a variation of your code that is specific for the test environment. So what I recommend is keep the 3 layers extremely separated. And in case you want to test something from Roboelectric into the JNI layer, it's just testing that the method that you call don't throw an exception. Because in this way, you are keeping safe your signatures. Because every time you refactor whatever, Android Studio is not going back and refactor for you the JNI layer. And this is very error prone.
Smoke testing all the JNI methods, but not necessarily multiple combinations.
Yes, not necessarily multiple combination. Other questions? So the description was promising a fart app. I'm sorry if I disappointed you, but just in case, the slides will be live and you can play with it. It's loading also in the slide deck. And thanks so much.